Hi there, and welcome to another Tech Tips Tuesday. In this episode, we're going to take a look at alternating current, and then we're going to also check out a few ways of changing that alternating current into direct current. Then we'll talk a little bit about filtering and why those capacitors are needed after the rectifier. So let's get started. One very key thing to make you proficient in electronics is your ability to visualize the way things work just by looking at certain circuits. Now, I'm not talking about looking inside a computer or inside of a piece of vacuum tube gear and seeing all the components and understanding how they work. I'm just talking about looking at schematic diagrams. So when I look at a schematic diagram like this, I can actually see this circuit functioning just by looking at it. Basically, my brain is animating how this circuit works. And that's what I'm going to try and share with you in my series of videos. So I understand that having all this stuff on a whiteboard sometimes just isn't enough. You can explain all this stuff and have math written down and things like that, and it's still kind of difficult. So what I've done with this is I actually have made a jig that's animated that will show exactly how this whole entire system works. And that should better help you put a picture inside your head of exactly how the diodes are switching and how the AC is working. And we'll take a look at that just after I explain what's on the whiteboard here. On the whiteboard here, we're going to talk about some simple rectification techniques, and we'll start with this full wave bridge rectifier circuit here first. So really what we have here is a transformer running into a full wave bridge, and then we get DC out of this. This is what the DC looks like before it's filtered. So what I'll do is I'll start with the AC here. So say we have 120 volts RMS AC at 60 cycles running into here. 60 cycles is the standard frequency for North America. Okay. So what that means, 60 cycles per second and 60 hertz are the same thing, all right? So we have 120 volts here, and it's oscillating at 60 cycles per second. So that means that it's changing polarity. It's going positive, negative, positive, negative, positive, negative, positive, negative, and it's changing back and forth. Now that isn't a very abrupt change. It's a nice smooth change because we have a nice smooth sine wave. It's not a square wave change. It's not like positive, negative, positive, negative. It's not like that at all. It's a real nice smooth transition. Okay, now that goes into the primary winding inside this transformer. All right, now since this is at 60 cycles, we're going to have a fair chunk of core size here. If we have, if say we had a 5 amp power supply or something like that, we're going to have a pretty large transformer. And the reason that we're going to have a large transformer is because the frequency is so low. As the frequency goes up, the core size goes down in transformers, and it also changes material as well. So just for now, we'll call this an iron core transformer, and this is the secondary side winding, okay? Now there is no connection between the primary side and the secondary side winding. They're only coupled by magnetism, really, okay? So how a transformer works really quite simply is as this is oscillating, as it's changing, all right? So we have positive here, negative here, say up here and here, okay? And it's changing, okay? It comes to zero, all right? So basically the magnetic core on the transformer is collapsing. And then, of course, this is changing direction, so we get a rise again on the field. Now, as the field on the transformer is rising and collapsing as this is oscillating, that induces the actual oscillation, the rising and the collapsing of that magnetic core is inducing a voltage in the secondary winding. So right now I've got this written as a 1-to-1 transformer. So if there was 120 volts AC on this side, there would be 120 volts AC on this side in an ideal world, okay? All right, so usually when you have a transformer written and it's a step-down transformer, you'll usually have fewer turns on this side illustrated in a schematic. I really didn't have any plans to label this as anything, so we'll just use it the way it is. All right. So now we have voltage on this side. So basically what we have now, if this was a 1-to-1 transformer, we'd have an isolation transformer is really all we'd have. All right, the advantage of having transformers is that we can take higher voltages and drop them down, or we can take lower voltages and raise them up. All right, so whenever you take a voltage like 120 volts and you lower that voltage down, you gain current, but you lose voltage. All right, and it works the opposite way. If you step voltage up, you gain voltage, but you lose current, and that's just the way things work. All right, so here we have AC on this side now, and this is alternating just like this side here. Nothing has changed, it's just gone through a transformer right now. This winding here is going into a bridge rectifier, and what this bridge rectifier is doing is it's changing this to pulsating DC. Now we have all sorts of different kinds of rectifier setups. We have full wave bridge, we have half wave bridge. We have all sorts of different ways of doing this, all right? So what's happening here is, I'll just try and illustrate this, all right? Say this is positive and this is negative right now, okay? What's going to happen is this diode here is going to conduct and this diode is going to conduct. So we have the positive going out here and we have the negative going to earth right here or to ground right there, all right? Now, of course, we're going to get a pulse out of this right now, all right? So now as this changes, all right, so now this is going negative and this is going positive. This diode is now conducting and this diode here is now conducting. So you can kind of see what we have. We have the rectifier doing this, and it's doing it on both halves of the cycle. It's doing it on this half and on this half of that one cycle. So we get very little gap in the actual rectified DC, okay? So basically what happens is that we've got, you know, pulsating DC up here, and that's still hum. Now this is acting as a frequency doubler, because what it's doing is it's taking this half of the cycle and putting it up on top. So instead of having, for a half wave, we have this here, and then of course this is missing, and then we have this one here, and then this is missing here. This is 60 cycles still, right? Because this is one full wave right here. So it's counting this as 1 and 2 and 3 and 4 and 5. This is taking the bottom half here basically and putting it up here as well. So we get a frequency doubler out of that. So that's why you hear 120 hertz buzz out of a full wave rectifier if the capacitors are bad. Now the job of the capacitor is really quite simple. What happens is as this is charging, all right, so what's happening now is this is changing and the voltage is starting to rise here, okay? It rises and then of course it comes to 0 and then it switches polarity again, all right? And that comes to 0 and it switches polarity again. So we have this buzz here and we have this area right in here, okay? And that's between the pulses. Now the idea of the filter capacitor is to fill these in. So what happens is when this rises, this is also charging this filter capacitor up to this point here, all right? And then as this goes down, the charge on the capacitor is enough to carry it to the next charge cycle again. So in effect, you can see how we would get clean DC here. All right, so what would end up happening with this right here, okay, if we put too much load current on this particular portion here, what's going to happen is we're going to get a dip, because the value of this capacitor here has to be large enough for the load that's being drawn, because if there's too much load being drawn, when this starts to go down, the capacitor isn't going to be able to fill that gap anymore, and it's going to drain that capacitor off as well. So on the next cycle, it's going to charge that capacitor back up again, and then of course, if there's too much load, it's going to pull it down to a certain point again until it can charge it. So that's why you see in very large linear power supplies, like, you know, say a 30 or 40 amp power supply, you've got this really, really big can capacitor inside there. And that's because it needs to hold this area when you're pulling very, very large current. That cap can't drain. It has to act like a battery and hold that up there until the next charge cycle comes again. So this is full wave rectifiers. This is a full wave situation. Now, if you look at a half wave rectifier, look at the distance between these. Look at the actual distance between these. This is why for half wave rectification, you need a much larger filter, because you have to hold this whole area. You have to fill this entire area up right here. It has to hold that up to this line as this is going on the bottom half of the cycle, because there's nothing to fill it up. If this was full wave, you'd have that extra lump here and you'd only have to fill this little area here. But you've got this really large gap. And that's why, again, you know, half wave rectification really isn't preferred in large power supplies, because you'd have a really huge capacitor to fill up this gap. You know, you'd almost need a battery sitting there or something to keep it up at that level. And that's what a capacitor does. The capacitor is just acting as a filter, and they call it a filter, but really what it's doing is it's, you know, filling in the potholes in the road there, really is what it's doing. So, and again, if you start to pull really heavy load at this point right here, it's going to want to pull that down until it gets to the charge cycle again, and it's going to want to pull it down until it gets to the charge cycle. So the whole idea, whenever you're designing a power supply, is to have enough capacitance here so that, you know, no matter what kind of load it's going to deal with, it's not going to be able to pull that capacitor down. Now you have to remember that the power supply has to recharge that capacitor as well as feed the load. So you have to understand that these diodes have to be very, very large in a high amperage power supply in order to do that. It's not only powering the load, but it's also recharging this cap here to its max for when, you know, when this actually goes back down to 0 again and then comes back up. It's going to have to again charge that capacitor up to this point, and so on as it goes down the cycle. So that's why full wave rectification is, you know, a bridge rectifier is really preferred in, you know, linear power supplies or something like that. Now you'll also notice in some of the really large switch mode power supplies, they got really low value capacitors, and you're thinking, well, how come they got smaller capacitors? Well, they run at such a high frequency that this is reoccurring so incredibly fast that you don't need all that capacitance because it's there all the time. It's moving so incredibly quick. It's recharging that cap at an incredible speed. That's why you see in really, really high frequency switch mode power supplies, you don't see that many microfarad on the capacitors. It really is quite low. So that's the reason for that, just the speed. It's charging it so incredibly fast. All right. So that's that. So now here we have a different kind of rectifier, and this is what you find in a lot of the older radios and a lot of older equipment that don't have a bridge rectifier. This is still a full wave rectifier, but what's happening here is you have half the voltage of this. So here, just for argument's sake, say we have 20 volts here from end to end, all right? If we have 20 volts from end to end here, we're only getting 10 volts here because it's from here to here. This is the ground here, right? So we have 10 volts here and 10 volts here. All right, now of course, when we rectify it, the voltages change and everything like that. Another thing I should mention is I'm talking about RMS voltages here. Whenever you're looking at voltages on an oscilloscope, it's usually measured in peak to peak. So if you have any older oscilloscope that doesn't actually, you know, say RMS and doesn't do the math for you, it's always peak to peak or peak voltage. So if you were to use the peak to peak voltage, say, to give you an idea, say that this here was 10 volts peak to peak. Let's just use that. That's a nice easy number. Okay, 10 volts peak to peak, and you're measuring that on your oscilloscope. Okay. To get the RMS value, you have to go 10 times 0.3535 will give you the RMS voltage. So technically you would have 3.535 volts. That's what it would be. So 3.535 volts is what you would have RMS on this side. So it'd be really low if you were to measure that with your voltmeter. Okay, so your AC voltmeter is most likely going to measure RMS volts, and that's what you would see. Whereas if you used a peak-to-peak reading oscilloscope, you would see 10 volts peak-to-peak at that point. So if you ever want to convert peak-to-peak to RMS, that's what it is, 0.3535, and you'll get your answer right there. Okay, so I'm talking in RMS, and I'm talking in peak-to-peak, so I can see where that would get a little bit confusing. All right, so just say here we had, just say 10 volts here and 10 volts here, right? We're still at this point, right, it's still 10 volts because it isn't 20. Our ground is right here. And this is a different rectifying scheme, but it still works the same way as this. If you were to ignore this back half of the diode here and put a ground there, this would still be switching like this. Okay, it would be going back and forth and back and forth and back and forth like this. So still, it's full wave rectification. It's using both halves, whereas as you can see here, this is half wave. We only have one diode here, and then we're only getting half of the wave. So what I'll do now is I'll take what I've shown you here, and we're going to head on over to the bench, and I'm going to show you this in action, show you actually how it looks. And I'm going to slow the frequency down. I'm not going to use 60 hertz, and I'll show you what it looks like with a really slow frequency so we can actually see the diode switching, and we can see what the AC is doing as it's reversing. All right? I have my function generator hooked up to my little test fixture here, as well as the oscilloscope. The function generator is running at 0.09 hertz, so quite a bit slower than 60 hertz, but that allows us to see the function and the switching action of what's going on the AC here. So the oscilloscopes are hooked up to, well, this one here is hooked up to the function generator, and this one here is hooked up to the output of this half-wave rectifier. These two LEDs here are bicolored LEDs, and they're just showing the AC moving back and forth. And this is an actual bridge rectifier made out of LEDs. And this is the output, indicating the output pulses, this one here and this one here. So you can see on the positive half of the cycle, all right, this LED is on, whereas on the negative half of the cycle, it's off. You'll see this one come on here again quite shortly. Now you'll notice that this one here is turning on even the negative half of the cycle, and that's because this is a bridge rectifier where this is only half wave. So as this one here is on the positive half of the cycle, it turns on, and now that it's on the negative half of the cycle, it's also turning on again. You can see the negative half of the cycle here. And that's just because this is switching this around. It's continually switching that around so that we continually get positive pulses. So you can see when this is negative, this diode is on, and when this is positive, this diode is on. And when the polarity is reversing, this diode is on for negative, and this diode is on for positive, and you can see the path. So we have a path here, and a path here. And we have a path here, and a path here. And that's exactly what this is doing. It's just acting as a switch, except it's doing it much, much faster in real life. This is just slowed right down so we can see the action. Now you can see on this one here, it's only actually giving us output on half of this cycle here. The other half of the cycle, it's completely off, as you can see down here. You can also notice the very large gap. That's where the negative portion of the cycle would have been. And that's the difference between full wave and half wave rectification. So I can speed this up just a little bit here. We'll say 0.5 of a hertz. So you can see how this is acting as a frequency doubler. This is, on every one, whereas this is missing the 1/2 of a cycle here. So if I turn this to 1 hertz, that would be 1 pulse per second. So I'll turn up to 1 hertz. So you can see that's at 1 hertz, and this is at double the speed, 2 hertz. I've got the scope probe hooked to the full wave rectifier here, and you can see that we're on the down part of the cycle, and it's still giving us a positive peak, and that's because this full wave bridge rectifier is switching that around. Mangled up the paper just a little bit here when I moved that scope probe around. You can see here, we have a peak here, and then when the other two go, we have another peak here again. So really what it's doing is bringing this bottom portion onto the top up here, acting as a switch. So no large gaps here, much easier to fill this with a filter capacitor. So now what I'm going to do is I'm going to speed things up, and I'll give you an example with an actual capacitor. I've got 60 cycles coming into this now, so it looks like all the LEDs are on at the same time because they're moving so incredibly fast. So this is full wave here, and what I'm going to do is I'm going to add a capacitor that's not enough capacitance to actually smooth this. Okay, so I'll add a small capacitor here. And as you can see, what's happening is, move the trigger, steady it up a little bit. So what's actually happening here is this is charging with the cycle, but it doesn't have enough capacitance to hold it as it's going through. So the LED in here is actually pulling this down, the LED circuitry, and there's a resistor in there that's actually pulling this down. So not enough capacitance, so we still have quite a bit of ripple here. All right. So you can picture that as it's, coming to the top here, and then it doesn't have enough staying power, not enough capacity, so it's draining the capacitor off, and then it's riding the next peak up and then doing the same all along here. All right, so what I'll do is I'll add a different capacitor here. I'll add this 330 microfarad capacitor. As you can see, we're getting pretty close to being filtered, but you can see there's still a little bit of movement there. So if I load this, you know, we're definitely going to see some ripple because this is going to discharge that capacitor. So really what I'm going to do is I'm going to put a heavier load across this. I'll just put that on here. And as you can see, we get quite a bit of ripple because it's just loading it so hard. So again, that capacitor is discharging and it's being charged up again and discharging in this particular area here, or in the small area that's in between the peaks here. So if I do this area in between here, it's discharging, and then it's charging back up again with the next cycle and discharging, and so on and so forth. So if I add a lot of capacitance here, you can see that we pretty much get smooth DC, and that's with 1000 microfarad. So that's what the capacitor does, really. It's just holding it up here, kind of like a peak detection circuit. So now what I'll do is I'll switch the probes around to the half-wave rectification circuit, and we'll check that one out. Alright, I've got half-wave rectification hooked back up here again. And what I'll do is I'll hook a filter capacitor in line with this. Alright, same value there. And you can see we still have ripple with this. Alright, you can see that ripple kind of moving across here. So what I'll do is I'll load it just a little bit more, and we should get just a little bit more ripple out of it, indicating that we need a much larger capacitor. You can see that, how it's coming down there. So I can hold this here. Let's see if I can hold it. Put this back on here. So you can see it's charging up on the cycle there. I'll just move the trigger down here. You can see it's charging up on the cycle here, alright, and then it's falling because of the load here, and then it's charging the cap on the next cycle, and then it's discharging and falling, and doing the same all the way across here, indicating that we need a much larger capacitor here. So I'll just remove that, and we can see the half-wave rectification again. Now, if we wanted to look at this as that third rectifier that I showed on the bottom, a full wave rectifier with a center tap, all you would basically do is just cover this up here, and you would have the center tap here, and the way that these diodes work would be the exact same function. They would just be going back and forth like that, and this would just be at a continual ground here for that full wave rectification there. I hope you enjoyed this short demonstration on alternating current and direct current. If you did, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos just like this in the very near future. So until that time, take care. Bye for now.